let's see. All right, so just the general review you have on that first slide there is just that thing we've seen several times about amplitude, period, phase shift, and vertical shift. So, so those are all going to be the same for these. You're going to find we can use sine or cosine for most of these problems. In general, most of the time we use sine. On Desmos, you can actually use sine or cosine, and it does not matter. But you'll find we use sine most of the time. If you were doing it on the actual calculator, the calculator will only do it using sine. It will not do cosine for you. So we usually use sine instead of cosine when we're doing these problems. So talking about things that can be modeled with sinusoidal functions. Several examples here. The amount of daylight that you have during the day. So that would be, in the winter the days are shorter, in the summer they're longer. Then they go back again. That just goes again and again and again. Ocean tides are going to be roughly measured by sine graphs. I've done projects with this before, but I don't think we'll do it this time with using like the data from the NOAA website where you can click on most any coastal area, and they can give you the height of the ocean tides, and you'll see that it goes up. Now, in that project one time, I let them choose wherever they wanted, and some of the students chose a area that had just had a hurricane come through. So their data was all over the place, crazy, and did not make a very good sine curve because obviously a hurricane coming through affected what the tide levels were. But if it's just normal, they'll be roughly sine curve. Temperatures. This could be roughly temperatures throughout the day, like it's cooler in the morning, hotter in the middle of the day, cooler again at night. That's not going to fit as well because, of course, we have major variations in weather. But certainly, it's cold in the summer, warmer in the, it's cold in the winter, warmer in the summer, cold again in the winter. That is going to fit a sine curve really nicely. Basically, anything that is periodic, anything that repeats itself, is going to be able to be modeled using a sine curve very well. Some things I'm less familiar with because they're a little less accessible, but if you were like analyzing waves or anything like that with physics, sine curves come in well there, but they're just a little, our applications usually don't go that direction just because sometimes people don't have the physics background to deal with that. So, here's your notes we've just started. You haven't missed much except for going over homework. All right, so I left the calculator instructions on here. Do I want to teach you how to do it? Let's do both. Let's do both. So, if you don't have your yellow calculator, grab it, your TI-84. Let's do both. I've just about quit using the yellow calculator with Math 1 at all because Desmos is so much easier for them to use. And really, Desmos is fine. The only reason that I feel like I might need to teach you the yellow calculator, the TI-84, is that when you go to college, it's all going to depend on your professor. If you have to take a class where you're doing something like this, and there's a chance that you're going to have to use the TI. There's probably a pretty good chance you're going to have to use the TI-84 because they might not want you to use the Desmos because you have to use the internet. Although, there's a test mode you can download that I'm thinking about piloting with you guys. It like locks your phone out while you're using it, and it might would work, because Desmos is better. It's just easier to deal with. So let me get the calculator though. We're going to learn both. And I will allow you to use either whenever we do problems on this. So if you prefer one over the other, you don't necessarily have to use both. But I would like to at least expose you to both here. And the calculator and Desmos use slightly different algorithms, obviously. Sometimes the answers are just a little bit different. Usually it's a very small decimal difference where it's not really going to matter. But they are a little bit different. So if we're going to use the calculator, we need to first enter our data into L1 and L2. Do you guys remember what we hit to get there? Stat, edit. All right, so stat, edit, and then I don't know that I have put, look at this, I have not put anything in this calculator since I did this last semester. I have not used this to do one single regression since I did this last semester with pre-cal. I don't think, because this is the data that is here that I already have. I don't even have to type it in. But if you have stuff in there that needs to be cleared out, if you go up to the L2, make sure you hit clear and then enter. Don't hit delete or it'll get rid of your L1 and L2 altogether. So you want to enter your data here. Let me make sure I didn't enter anything incorrectly. Line here. All right, so and to get to the L1, L2, you just hit stat and then edit. It's going to be the L2 over here. Yes. What's your question? Oh, yes. It's one chart. It's just going to the next line. So, yes, all the way through 12. So I don't hear too many calculators clicking away anymore, so I think that we have mostly got those in. So once you have your data entered in, you're going to go to Stat again. You're going to go over to get to the Calc menu. And then we're going to go, I think it's the very bottom one. We're going to go all the way down to the bottom where it says sign reg, or if you just hit the up arrow, it'll take you to the bottom of the list. So C, sign reg, is the one we're going to choose. So from here, if you guys, several of you have the newer calculators, it is going to have like a different menu here. It's going to say like, maybe like X list, Y list, something like that, store, and then calculate or something like that. So L1 is what you want for that X list. L2 is what you want for the Y list, which I believe it's already going to have. If you want to store this in Y equals, which a lot of times we might want to do, from this calculator, you're just going to do vars. Go. So vars is right here beside of clear. Y vars. Go over to Y vars. And then function Y1. So I'll write that down. To store, and you'll go to vars, Y vars, function, and then Y1. Sometimes you don't really need to store it. It just depends on if they're using that to ask questions. Oh, I think you might be in a weird mode. Let's see. Do not know about iterations. I would just go with what you got there. I'm not sure what that iteration is for. I don't know if I've just ignored it all my life when I've seen it. I've never had one of those calculators personally. Or if that's something new I should know about. And then you're just going to hit enter. Or if you have the fancy calculators, you go down to the bottom where it says calculate and hit enter. And hopefully it's going to give me what I'm supposed to have here. It looks like I've got what it gave me last time, so that's good. So has everybody got their sine regression working for everybody? Good. All right, so this is how you do it on the calculator. This is the reason I don't like to do it on the calculator. If you now, you can see like in y equals, you have this, so you could go to the graph. But the graph is just so much harder to deal with because like a graph this, I've got nothing. I got to zoom out. I've got, it doesn't label this as like pi over 2, pi over 4, those sort of things like it does on Desmos. So if you ever have to look at the graph, I just strongly prefer Desmos. I think it's much easier to work with. But if all you need is the equation, the calculator works fine. A lot of times that is all you need, so that'll be fine. And you may have teachers that don't let you use Desmos for some of this, so one day. I will let you use Desmos on any of these we have. So that is our directions for the calculator. Let's try it now with Desmos. So pull up Desmos here. So to add data on Desmos, you're just going to hit the plus. You're going to tell it table, and then we're just going to enter the data here. See how much better the graph is on Desmos. It just shows up automatically. You can tell what everything looks like. It's easy to zoom in and out. It's just generally a lot easier. It shows up as you graph it so that you can see, because one of the main things, the main reason I see kids miss these problems, because they're pretty straightforward, is that they have typed in one of the numbers wrong. So if I type this 11.3 in as a 1.3, it'll throw my answers way off. But on Desmos, you a lot of times catch it because you've got this point that's just in a really odd spot, right? On the calculator, you might be a little less likely to catch it because you don't see the graph quite as easily. All right, and so all you have to do for this is you're going to just type in y1 squiggle a sine bx1 plus c plus d. So it's just that standard form of a sine graph with A's, B's, C's, and D's. Make sure you put a 1 after your Y and a 1 after your X, and use the squiggle instead of an equal sign. It will automatically make the 1 a subscript if you type just X and then 1 after it. And all of our rounded values on this match our calculator values, I'm pretty sure. But you can see right here, like for this B, I'm getting 0.511958, and right here I got 0.511969. The C is also slightly different. The D is exactly the same. So where Desmos uses a slightly different algorithm to calculate this, you're going to see slight differences sometimes. It should not affect your answer enough for it to make it not work for the quiz. I believe on the quiz I have set it so that there's like a really slight margin of error. So if you maybe if it causes this to round to an 8 instead of a 7, that because you use the calculator instead of Desmos, it should not count it wrong for that. But if it does, I'll go back and look at it. And like I said, I just like Desmos a lot better because here's your graph. If you want to know something about that graph, if you want to know the y-intercept, if you want to know, whatever you want to know, it's a lot easier to find. Okay, so we are now going to look at just generally finding amplitude, period, phase shift, midline with all these decimals instead of having numbers, and then we're going to talk about what that means for this problem, right? So this is our equation that we got. We're just going to use these numbers rounded to 3 decimal places. It would be a little more precise to use all of them, but that's okay. So for our amplitude, Maddox, what is the amplitude of this graph? Very good. All right, let's see. Bronwyn, how are we going to find the period of this graph? Good, 2 pi over b. And what's our b for this problem? Very good. So we're definitely just going with decimals on this because we have decimals in the problem. And I'm getting 12.2718 whenever I do that. Okay. Caitlin, what about the phase shift? How do we find it? C over B. So what's our C for this one? And B. And so 1.603 divided by 0.512 is going to give us 3.13086. And would that be to the right or to the left for this one, Caitlin? Right. And Blaine, what about our vertical shift or our midline? Those really kind of go together. It's our 12.116 up, which means our midline is y equals 12.116. Okay, any questions on finding those? Exact same as we've been doing, you just have decimals with them. And I'll talk about what they mean for the problem. So, the midline is at y equals 12.116. What does this mean within context of the problem? Okay, so one thing I like to think about here, on that table, here I had months. That was my X right there. And then my Y was daylight, right? Is that what we're doing on this one? Yes, hours of daylight. So whenever I'm talking about Y equals 12.116, I'm saying that hours of daylight is 12.116. So what does that mean? What is that for the context of this problem? What do you think, Callie? Average, yes. So the average amount of daylight is 12.116. And your midline is usually going to be your average of whatever the y coordinate stands for, right? Okay, amplitude is 1.598. What does this mean within the context of the problem? It is your variation from that average, right? So the amount of daylight varies 1.598 hours from the average. So we might be 1.598 hours more than the average 12.116. I should put hours. Or we might be 1.598 hours below the average. All right, the period is 12.27. What does this mean within context of the problem? It repeats every 12.27 what? What would I measure 12.27 in? Months. This period is talking about our x-axis there. So period tells you how often this is going to repeat. Why is there a phase shift of 3.13 to the right? This one is not as much of an intuitive answer here. The answer is simply this. If we go back to that Desmos graph right there. On my graph here, looks like it's our minimum point right there. It's happening pretty close to our x-axis. It's actually a little further over, but it's pretty close to our x-axis. So, and y-axis. So 0 here is our shortest day. When does the shortest day occur? It's December. So it happens in December. So for this, that has to be shifted so that it lines up here because they're giving you 1 as January. So we have to shift that a little bit because especially, remember, we're using a sine function here. So if I type this in where it was a sine function without, exact same sine function but without the phase shift, y equals 1.59834 sine of 0.51158 0 for a sine function would be your equinox, right? Whenever you're in the spring and in the fall, whenever your days are about the same. So we need this 0 here to be shifted over here, so that this minimum here is shifted over so that that is happening in December and not in if we did not shift this graph, then in December, right here at 0, we would be at an equinox, which is sort of the opposite of true, right? We got the shortest day. So it's really pretty much always this answer if they ask you about phase shift. It's pretty much always this answer. Why is there phase shift? It's just so the data will line up. If we were doing this by hand, we might actually look at those points and decide that we wanted to use a cosine instead because we started at that minimum point or pretty close to starting at that minimum point. With the calculator, in general, we just want to use sine with the calculator because the actual calculator will only do sine, and because it's just more standard to see it that way. So phase shifts will be necessary, but they really don't have a lot of significance other than just making sure the data lines up there for these. So here's our next example. So either on your calculator or on Desmos or both if you want. I want you guys to find the sinusoidal model for this. And when you see that sinusoidal model, that just means a sine function. I'm pretty sure, let me look that up. Pretty sure sinusoidal can also refer to let's see if sinusoidal also refers to cosine. I think sinusoidal generally refers to just sine, but okay, so the other thing I really like about Desmos is I didn't really have to do a lot of work here. I just changed my data and it automatically adjusted. I didn't even have to type that back in. I don't see the graph here, but if I hit the wrench and change that y-axis to maybe like 75 or so, then I can see my data. And you can see these don't fit the sine curve perfectly because when you're looking at average monthly temperatures for Seattle, Washington, you are not going to always see the same pattern every year. If you add more years in here, you could probably get a curve that was even better. Maybe this was a particularly warm, time for them. Although this makes me, I wonder if these are average high temperatures or just like average temperature altogether. Because surely Seattle's average high temperature is not 66 degrees in August. It's kind of rainy. And I think they have the best one. We'll look at that later. Alright, so our model, let's write it down, turns out to be y equals 11.836 sine of 0.55. I'm going to round 555 x minus 2.452 plus 53.360. I rounded everything to 3 decimal places. That's fine with me. I'm pretty sure on the quiz tomorrow, whenever you have to do this and type in the A, B, C, D, I want you to round to 3 decimal places on that. So, those of you that did the calculator, did you get anything different? Is it significant? So it will sometimes be a little bit different, but I will set it so it'll take either one. So either is fine. Okay, so let's talk about what these mean. And I think whenever I made these slides, when I made these slides, because I've been using this for a while, I definitely used the calculator because Desmos did not exist. So I have the one probably that Blaine has here that is slightly different there, but it's generally very close, and we're going to get pretty close answers. Where you will see some variation is when you start plugging numbers into this, you'll get answers that are a little bit different based upon what you're plugging in, but that is why I'm not going to ask you for the equation and then also ask you to use the equation for something. It would still be really close and probably good enough for whatever you're doing, but it will be a little bit easier if we just have the equation given to us. So, what is the midline of this function? So, the midline for this function, Braden, what are we going to get for that? And in this particular context, what would we, let's see, hold on, let me look at my questions real quick. Let's see. Also, I wonder what's happened to Noel. Okay, what units would we use for that? What, it's 53.355. Is it in months or temperature? What'd you say? Fahrenheit, degrees Fahrenheit. And so that is our average temperature in Seattle for the whole year, right? The overall average. Amplitude for this model. Blaine, what's the amplitude going to be? And that's also degrees Fahrenheit. We're going to go that much above and that much below our average. There should not be a question mark there. There should be a comma. So according to the model, which means we also need to lowercase that W right there, what is the highest temperature? What about the lowest? So when it says according to the model, it means the equation, right? It does not mean go back to that table and tell me what the highest number is and what the lowest number is. So when we answer these questions, we're asking them from the equation that we have gotten. So according to the model, what is the highest temperature, what is the lowest temperature? If you did this in Desmos, there is another advantage to Desmos here. If you did this in Desmos, you can actually do this without really thinking very much, because it's going to give you a dot at that maximum point, which is 65.196. It's also going to give you a dot at those minimum points, and you'll get 41.524. But let's say that you did not use Desmos, or that it, for whatever reason, shows up when you can't use it. I don't think you'll see that for me, but the other way that you can do this is we can just take that midline, 53.355, and we can add the amplitude, 11.837. And whenever we add those together, 53.355 plus 11.837 is going to give us 65.192. Slight difference from Desmos just because of the rounding difference. Model is the graph of this equation, not the dots that were plotted. So whenever we look at this in Desmos, where'd Desmos go? All right, so when we look at this in Desmos, the model is that black line that I have up here. It's the graph of that sine curve that's given by that equation. The dots, the green dots, which are also, can be graphed there with this, those are your data points. So, so the data points is not what we're talking about here when we see the model. I will generally never ask you to just tell me the highest and lowest number from the table. So, and I also am not going to give you these questions together. So I'll just give you like the equation, and you'll have to tell me this on the quiz, mostly because if you mess something up with your table, it's going to mess up all your other answers. So, but when it says according to the model, it's talking about that there. And our lowest temperature, we do the same thing. Oh, let me go back to mode. We do the same thing, except for we would subtract. And whenever we do that, we're going to get 41.518. And these both would be in degrees Fahrenheit. Okay, here. All right. Okay, so for this, we also want to know what the period of this function is. So for our period, we just have to do 2 pi divided by b. B is going to be that 0.554. So 2 pi divided by 0.554 is going to give us 11.3415. Okay. All right, so that is what we get for our period for this data set. F asks, according to your knowledge of nature, what should the period be? It should be 12 exactly, right? Because our seasons repeat every 12 months. So it should be 12 months. And if we had more data, if this was over 10 years instead of just 1 year, we would probably see that period be closer to 12. You'd probably, have to have infinite data, and climate change could possibly mess that up as well. But in general, we would see very close to 12, probably a lot closer to 12. But something like having a really warm August could cause your data to be skewed a little bit. That's going to change that from being exactly 12 months. But in general, even considering climate change, because whenever we talk about climate change, they're not talking about it being 40 degrees hotter. Not 40 degrees hotter in the next year or two, right? It's very tiny increments over time. So even including climate change, we'd probably still see with more data this be a lot closer to 12 here. So according to your model, what is the average monthly temperature in July? Is it the same as your actual data? So when this says according to your model, what's the average monthly temperature in July? It's not asking us to look at the table, right? It's asking us to compare it to the actual data from the table. What do we do with this model to make a prediction for July? If we need to predict at any point, what does our X stand here for? We're just plugging in, because this is our number of months, and July is the 7th month. So if we just plug in 7, 11.837 sine of 0.554 times 7 minus 2.450 plus 53.355. We will get our answer. And I got 65.0715, and something I just thought that I need to mention right here. Whether you're in radians or degrees matters. For this, it would change your answer. So I am in radian mode, which in general for regressions, I just want you to be in radian mode every time. One of the big reasons for that is because everything we've done, like finding the period of the function, we've been doing 2 pi divided by 0.554, right? We could do that in degrees, but if we did, we'd have to do 360 divided by 0.554. So everything we've been dealing with, we've been using radians. It doesn't really affect the amplitude or the midline, but it does affect your period and your phase shift. So in general, just be in radians all the time for these problems. If you are over here with Desmos, another cool thing about Desmos, if I want to know whenever x is 7, I could plug it in, or I could just type x equals 7, which you can't do on your calculator, and it'll give you that intersection right there. And with this one, you get 65.081, which is a little bit different than what I got, but it's due to that rounding. And I did round this number off as well here, which is throwing it a little bit off. But this, I believe, is in radians too, because it's, oops, I didn't mean to do that. Yes, we're in radians. So, in general, you want to be in radians for this. All right, we got one more to do. Maybe we'll have time to do a few problems for your homework. So, this one gives us information, and we're supposed to write a trig equation that will model the situation. So, in a certain coastal location, the depth of the water in the sound at high tide is 14 meters. The depth of the water in the sound at low tide is 5 meters. The last high tide occurred at midnight, t equals 0. The next high tide occurred at 11:50 a.m., t equals 11.833333 there. So, we have to write an equation for this situation. So, if we're thinking about what's happening here, high tide is 14 meters. That's our highest. So, we know that's the highest we will ever go. And low tide is 5 meters. That's the lowest we will ever go. And so, it tells us last high tide occurred at midnight, excuse me, which we're calling 0. So high tide at midnight. We know we've got this point right here. The next high tide occurred at 11:50 a.m., which would be 11.833. So I'm going to put, I will just put 11.83 repeating. That's our next high tide right there. So low tide would have to be halfway between this. We've got a graph that looks something like this. And we have to write the equation for it. So if we're doing this by hand as we're going to, because Desmos will not find you a graph with only 2 points. So we only have 2 points in it. It can't do a good job with this. You might could put the third point. We might try that here in a second. But let's do this one by hand. Should we use sine or cosine if we're going to do this one by hand? Cosine would be better because cosine has a y-intercept at a maximum, and this has a y-intercept at a maximum. So we don't have to phase shift if we use cosine. So I'm going to use cosine. I'm going to put a bx right here, but I'm not going to put a plus c because I already have a maximum at the y-intercept, so I know I don't have to phase shift. What is the... Let's do midline first, because you really need midline to get well, you can get amplitude without midline, but what would our midline be? It's right here somewhere, right? Somewhere between 5 and 14. How would we find exactly what it is? What? Perfect. Just find the average. 14 plus 5 is going to give you 19. Divide that by 2, and that is going to give us 9.5, right? So 9.5 is our midline here. So we're going to have plus 9.5. So just averaging your high and your low. So what is our amplitude? It is 4.5. Couple ways that you can get that. You can just 9.5 minus 5, just see the difference between those two, or 14 minus 9.5. Those will both give you 4.5. Or you could see the difference between 14 and 5, that would be 9. And if you divide that in half, right, because from your highest to your lowest, that has a difference of 9. And if you take half of that, that's the amplitude. Okay, so that takes care of the amplitude and the midline. We now need the period to be 11.83 repeating. So we're going to say 2 pi divided by b equals 11.83 repeating. So to solve this, we would need to multiply both sides by b to get that out of the denominator. So we'll get 2 pi equals 11.83 repeating b. And then we just got to divide by 11.83 repeating. And so 2 pi divided by 11.83 repeating is going to give me 3.427. So my equation is going to be y equals 4.5 cosine 3.427 x plus 9.5. Like I said, no phase shift is needed on that because we use cosine. I know Desmos can't do this with only, I know Desmos can't do it with only with only 2 points. Let's see if it'll work like this. So we know at 0, we've got 14. And then we know again at 11.83 repeating, we've got 14. So let's see if it will work. If we take 11.83 repeating and divide that in half, at 5.916 repeating, our amplitude should be 5 for our height should be 5, I should say. So let's see if that will, I don't know if it'll do this or not. So y1 squiggle a sine b x1 plus c plus d. No. See what it does here. Even if we add in other points, it tries to make that a minimum point. It doesn't recognize that that is repeated. So you'd have to add in more points for this. So this is one that really by hand would be better. And we use cosine, but even with cosine, it still doesn't like it. You see, it really gets it wrong there. So you have to have, I'm going to say, probably at least 4 data points. If we tried here, probably would, I don't know if it even worked. We put in the midline. Let's see. Let's try it. Let's just try it. 2.9583 repeating. That would be 9.5. It will. So you would, if you did it with this, you would have to. It does a good job there. You would have to have probably at least those 4 data points for that, for it to come up with something decent on that. All right, so your assignment that you're going to do for me for this one is